9.1, and we're going to talk about translations today. Translations are a specific kind of transformation. So first off, let's talk about what a transformation is. So what are we going to guess? What are we going to guess that a transformation, if we're talking about a transformation of a figure, what are we talking about? What is a transformation going to do? Change it somehow. Transforms it. So a transformation changes a geometric figure somehow. And we're going to talk about four transformations in chapter 9. So one transformation basically per section. The first three that we're going to talk about are called rigid transformations. And those are important when we talk about when things are congruent. So our rigid transformations we have three of them. First one is what we're going to spend a little more time on today, is a translation. So what are we going to guess that a translation is going to do to a geometric figure? And we think the word translation means. Doesn't have to do with language. Any guesses? So it has to do with movement. Translates it over. So translation has to do with, I think of it as a slide, so we're going to move or slide. So if I have a rectangle, a translation is just going to move it somehow. So translation is just a move or a slide. And we're going to get a little more technical, a little more mathy with that in just a little bit. A rotation. We'll talk about rotations tomorrow, I believe. What are you going to guess that a rotation is going to do to a figure? Rotate it. So, and we'll talk about how much something rotates, how to tell if something is a rotation of another. And the last one of our rigid transformations are a reflection. So what are we going to guess a reflection does? Flips it, reflects it. So and when we reflect, we kind of think of reflection having to do with a mirror. So we're going to flip it or reflect it over a line. And our line could be the x-axis, the y-axis, or some other line. So some line is like our mirror, and we're going to flip it or reflect it over a line. So those are our rigid transformations. These three rigid transformations are important because they don't change the size or the shape of a figure. Moving it around doesn't change the size or the shape. Rotating it doesn't change the size or the shape. And reflecting it doesn't change the size or the shape. And we're talking about a nice, perfect mirror here, not like a funhouse mirror. So a reflection is perfect. So we say that the rigid transformations preserve distance and angle measure. So when we do these transformations to a figure, the side lengths don't change and the angles don't change. So we're keeping it the same size, the same shape. We can also call a rigid transformation a rigid motion. rigid transformation, rigid motion mean the same thing. And rigid transformations, and the reason we call them rigid is because things aren't moving around. Everything stays exactly the same. Rigid transformations or rigid motion is important because that's how we make our idea of same size and same shape a little more formal. The two figures are congruent if one is a series of rigid transformations of the other. So that's going to be our more technical idea of congruence, is if we can take one figure, move it, rotate it, reflect it, put it right down on top of the other one and they're exactly the same, that is how we know that they're congruent. So we can do some series of rigid motions and we can put one exactly on top of the other. That's how we're going to define a more technical definition of congruence. And what we want to do in chapter 9 is be able to describe these transformations with using numbers. How do we tell how much we're moving something? How do we tell how much we're rotating something? How do we tell if something is a reflection? So we need a little bit of terminology, and then we will do a little practice with translations. So for transformations, our original figure is called the pre-image. And after the transformation, it is called the image. So in chapter 9 we'll talk about the pre-image and the image a lot. So the pre-image is the original, the image is what happens after some transformation. So let's take a look at a couple of examples that have to do with this idea of rigid motion. So for all of these examples, all we want to do is say, does this appear to be a rigid motion? If we're talking about, I'm going to write our pre-image and our image over here. So we'll do them in columns. So here's our first one. Here's my pre-image, and here's my image. Does this appear to be a rigid motion? That's a few people shaking their heads no. So what's wrong? What is this? Why wouldn't this be a rigid motion? It's not preserving distance or angle measure. The side lengths of the triangle on the image are smaller, so it didn't preserve the distance. And the angles are different. It didn't preserve the angle measure. And in everyday words, we'd say they're different shapes. Well, they're both triangles, but they're not the same kind of triangle. They're also different sizes. So that's how we say they're different sizes and different shapes. This transformation didn't preserve distance or angle measure. How about this one? Does this appear to be a rigid motion? If I could draw perfectly, does it appear to be a rigid motion? Got a few people shaking their heads. So it could be a translation and then a rotation, or a reflection and then a translation. So some combination of rigid motion would make this. So this would be, we said this one was a no, and this one does appear to be a rigid motion. We could move it, rotate it, reflect it, and get it to look exactly like this. How about, let's do one more. And I'm going to do my image and my pre-image a little differently this time. I'm going to put this one right in the middle. And if I could draw up here perfectly, does this look like it could be a rigid motion? A few people shaking their heads. What kind of rigid motion would take number 1 to number 2?
Rotation.
A rotation or a reflection. I could put a mirror here, and that would be a reflection. So this does appear, yes, does appear to be some kind of rigid motion. Preserves distance, preserves angle measure. They're the same size and the same shape before and after. So we have a pretty intuitive idea. Most of us have a pretty intuitive idea of what we mean by rigid motion. So to describe a transformation, we use an arrow, what we call an arrow and prime marks. So what we would say is that triangle ABC, for example, is transformed to triangle A prime, B prime, C prime. So we could say that triangle A prime, B prime, C prime is a transformation of triangle ABC. Or the other way that you'll hear this, that you'll see this written, is that triangle ABC maps onto triangle A prime, B prime, C prime. So our transformation takes triangle ABC to triangle A prime, B prime, C prime. So let's look at an example using this idea. So I'm going to say for this example that triangle ABC maps onto or transforms to A prime, B prime, C prime. Now let me draw my triangles here. So here's ABC, and here's A prime, B prime, C prime. Triangle ABC is the image, the pre-image. To use our other terms, and this is the image. So the question I want to ask here is, what is the image of angle A? So my pre-image is here. What would be the image of angle A? A prime. So it's asking what is angle A? What does angle A transform into? The image of angle A is angle A prime. That's the image of angle A. After I translate it over here, it turns into that angle. How about the image of angle C? What would be that image of angle C? C prime, angle C prime. And how about the image, let's talk about some segments. What would be the image of segment AB? A prime, B prime. Right idea. You just have a prime over with every letter. So the image of AB, segment AB, would be A prime, B prime. And the way we've talked about this before is we talk about the corresponding angles. So these angles are in the same place, the corresponding sides. We're talking about the corresponding sides and the corresponding angles. How about segment BC? What's the image of segment BC? B prime, C prime. So we're just matching up the before and the after, basically. And the way we talked about this before is the corresponding sides, corresponding angles. So A prime corresponds to angle A, B prime corresponds to angle B, etc., etc. Segment AB corresponds to segment A prime, B prime. Now with translations, if we're just sliding this over, it's usually pretty easy to pick out what are the image and the pre-image. Sometimes when we do rotations and reflections, it's a little harder to figure out. But we've done those kinds of things before when we figure out how corresponding sides and angles match up, to figure out congruent triangles or similar triangles, that kind of thing. All right, so now we have an idea of what we're talking about when we talk about transformations, how we write them, what they mean, image, pre-image, our arrow, and our prime notation. So let's talk about a little more detail about a translation. How do we describe a translation using math? And we decided that a translation had something to do with moving or sliding. And that's how we're going to define it. A translation is a transformation and the other way we talk about transformations is a rigid motion. Either way to describe it works. That the technical way to say it is maps. We can say takes, moves, slides. That maps all points on a figure the same distance and the same direction. So that's how we're going to define a translation. So what we're saying is if we take this rectangle and we want to translate it, all the points on the rectangle are moving 7 inches that direction. That's what we're saying. So this corner doesn't move a different distance than this corner. They both move 7 inches. And they both move in the same direction. If they moved in different directions, we end up stretching or changing the rectangle somehow. So a transformation is a rigid motion that maps all points on a figure the same distance and the same direction. So we're just moving everything the same distance, same direction. The way we write them, our symbol for a translation, T for translation, triangle ABC equals triangle A prime, B prime, C prime. So what we're saying here is we have a triangle here. We have another triangle that's a translation. And what I've done is I've taken that vertex and moved it to there, that vertex and moved it to there, that vertex moved it to there, and every other point on the triangles, I've moved them the same distance and the same direction. So if that's ABC, this would be A prime, B prime, C prime. And if I do that translation, corresponding sides and corresponding angles are congruent. So whatever angle, the angle or the sides on the image are congruent to the, are congruent to the angles on the sides on the pre-image. Just like we talked about, angle A is congruent to angle A prime, etc., etc. So these two triangles end up being congruent. So what I want to do next is do a couple of examples of how we tell, how we write out, how we figure out how much and in what direction, how far and in what direction we're doing a translation. So there's a way that we write that out, and we can describe translation using numbers. Let me grab I'm going to do a page in the back. Do this. There we go. So for this one, my example is we want to find the vertices. And here's my translation. The way we write translations with a specific distance and direction is we write it with little brackets like this, and then we're going to say -3, 4 of triangle RST. And I'm going to graph triangle RST here in just a second. So what this is telling me is that we are doing a translation. This is my X, and this is my Y. Translation -3 units in the X direction, and 4 units in Y direction. That's what the -3 and the 4 tell me. This is my X and this is my Y, saying we're moving -3 units in the X direction and 4 units in the Y direction. The way that we normally think of that is 3 left and 4 up. So I'm taking, wherever I graph my triangle RST, I'm going to take each vertex, 3 units left and 4 units up. That's what this tells me to do. So let me graph my triangle and we'll do the translation. I want this to be in blue, and I'll make my line a little thicker. Oops, I want solid lines. So there's my X and my Y. Make that straight. There we go. Straighter at least. So here's my triangle RST. So I'm going to go 1, 2. There's R, and its vertex is at 1, 2. S is 1, 2, 3, 4, 1. S is at 4, 1. And T is at 1, -3. So there's my triangle RST. So the easiest way to do this, when we have a graph, is we're going 3 units, we're going 3 left and up 4. So I'm going to go from vertex R, and I'm going to go 3 left, 1, 2, 3, and up 1, 2, 3, 4. And that's going to be R prime. And I look at my graph, and that puts me at -2, 6. I'm over 2 and up 1, 2, 3, 4, 5, 6. Do the same thing with S. going to go left 3, 1, 2, 3, and up 1, 2, 3, 4. So there would be S prime. And S prime puts me at, I'm over 1 and up 1, 2, 3, 4, 5. 1, 5. Same thing with T, left 3, 1, 2, 3, up 1, 2, 3, 4. And there's T prime, and that is point -2, 1. And there's my new triangle. So I can do this just by counting squares. Left 3, up 4. I can also do it directly from the coordinates of R, S, and T. So I could say that R prime equals, and I'm going to take the coordinates of R, 1, and subtract 3 from it. 1 minus 3, and I'm going to take the 2 and add 4 to it. That's -3 units in the x direction and 4 units in the y direction, and that gives me -2, 6. So I could do it that way and find that point. S prime, I'll take the coordinates of S, subtract 3 from the x, 4 minus 3, and add 4 to the y, 1 plus 4, and I get 1, 5. Just like I got right here. And I could say T prime, take the coordinates of T, subtract 3 from the x, add 4 to the y, and I get -2, 1. Just like I got here. I think counting squares is a little easier, but you can do it this way as well. All I'm doing is taking this number and putting it with the x coordinates. So subtracting 3, taking this number and putting it with the y coordinate, adding 4. That's what this translation is telling me to do. 3 left, up 4. -3 in the x, positive 4 in the y. -3 in the x, positive 4 in the y. For each one of those. Everybody good there? So when we have graphs, counting squares is usually easiest, but you can do it this way. So let's do one where we're going the other direction, where we have our graph, we have our image and our pre-image, and we want to figure out the rule. So here is, for our question here is, what is the rule for our translation? And our translation is going to take triangle LMN to triangle L prime M prime N prime. All right, so let me draw our graphs here. Let me get this line a little thicker. And I'll draw up our triangles. Let's see, L. Here is N, and there's N. So here's my triangle for this one. And let's draw the L prime, N prime, N prime. There's L prime. There's M prime. And there's N prime. So there's my transformation. My translation, we want to figure out the rule. So when we have a graph like this, just pick one vertex. And count. So it doesn't matter which vertex we pick. A translation moves all points the same distance in the same direction. So we can pick any vertex. Which vertex we want to pick here? L? Okay. So to get to L, from L to L prime, I'm going to go over 1, 2, 3, 4, 5, 6. I went 6 right. So I'm starting here, 1, 2, 3, 4, 5, 6, and up, 1, 2, 3. 6 right, up 3. So that's my rule. 6 units right, up 3 units, and I could pick any vertex and count that way as well. 1, 2, 3, 4, 5, 6, up, 1, 2, 3. 4 from in, 1, 2, 3, 4, 5, 6, up, 1, 2, 3. Yes? Yeah, so this, if L prime, N prime, M prime were over here, then we'd be moving to the left. And that's what we did, we go back here, that's what we did here. And that's why this number turned out to be negative, because we were moving to the left. Because our prime triangle was to the left. And we could move down as well. So if we move down, then the y would be negative. It's a good question. So we're going right 6, up 3. So our transformation, we have our transformation. We're moving 6 units to the right. We're adding 6 to our x, and we're adding 3 to our y. So this would be translation of 6 units right, up 3 units of triangle L, M, N equals triangle L prime, M prime, N prime. So that would be our rule for our translation. Positive numbers move us to the right and up. Negative numbers would move us to the left and down.
I'm so sorry.
All right, we good with that example? And we could do this one the exact same way. We could write out the coordinates of our vertices and figure out how much we have to add or subtract to get the other number. When you have a graph, I think counting, unless your graph is really huge and you have to count a whole bunch, you have a graph, you can just count the squares to figure out how you've done your translation. All right, let's bring this, just make it a little more kind of, not necessarily a practical example, but a little more something that we might be familiar with these kinds of translations. Let me get a different kind of page, and then we will be done. So let's say you leave your house and you go 2 blocks east, and then 5 blocks north. And this, let's say that takes you to a store. So you go 2 blocks east and 5 blocks north, and then you're at the store. And then, from that store, you go 4 blocks west, and 1 block south. How far are you from home? How many blocks from home? So we can think of the east and west like our x-axis, and the north and south like our y-axis. So we're going left and right and up and down. So 2 blocks east, 4 west, where do we end up? We go 2 blocks east and 4 blocks west. So if I go 2 blocks, if I go 2 blocks this way and 4 blocks, I end up 2 blocks west, right? So I'm going 2 blocks this direction, 4 blocks the opposite direction. So I end up with 2 blocks west. And then 5 blocks north, 1 south. So 5 blocks north, I'm going 5 up. We can think of it that way, and 1 down. So where do we end up? 4 north. So we end up 2 blocks west, 4 blocks north of home. So this is a way we would describe translations, and we're talking about walking around on sidewalks. Same kind of idea. We talked about how far left and right, how far up and down. So this, and we combined 2 different translations. Combine the first one and the second one, and we end up with this last translation: 2 blocks west, 4 blocks north. Questions there? Okay. So translations today, we'll talk about rotations, then reflections, and then there's one kind of transformation that we'll talk about that doesn't preserve length and angle measure, but we'll do those kinds of transformations, special kind of transformation, and that's how we end up with similar figures. So the rigid transformations give us congruent figures. The last kind of transformation, called a dilation, gives us similar figures. Right, homework. They erased all my boards over spring break. There we go.